everyone. In this video, we're going to look at another alternative method we can use to find limits at infinity. Again, let's take a look at what we already know about limits at infinity. We know that the limit as x approaches infinity of the reciprocal function 1 over x, we know that this is equal to 0. And the same thing as x approaches negative infinity. So the general logic here is as my x values get really big or very negative, this fraction turns into 1 over a very big number, which gets very close to 0. So I can get as close to 0 as I want by picking out an x value sufficiently large enough. Now there are other methods we can use to find limits even when it's not written in the form of 1 over x. And one of those methods is using the leading terms. So this is related to the end behavior of a function. Now just a reminder as to what that is. Let's say we have a function. I'm going to say this is h of x. And I'm just going to do a polynomial. So do 4x cubed plus 3x squared plus 2x minus 1. Okay, whatever this happens to be. The idea behind end behavior is that when x gets really big or really negative, so as we're approaching the ends of our x-axis, positive infinity or negative infinity, the end behavior of this graph is going to look like the end behavior for the parent function, which is just x cubed. So just looking at that leading term, we can have an idea on what the ends of the graph are doing. Okay. Now taking it one step further, we can apply that logic to rational functions as well. So remember, a rational function is a polynomial divided by another one. So we have two polynomial functions. I'll say p of x and q of x. So taking two polynomial functions and dividing them, I get a rational function. Now taking a look, I can determine the end behavior for this function in the numerator by looking at the leading term. I can determine the end behavior for the function in the denominator by looking at the leading term. So that means I can figure out the end behavior by comparing the two leading terms. So in other words, to relate that back to our limits, the limit as x approaches infinity or negative infinity, that's basically the end behavior. So the limit of this rational function, and we'll do positive infinity, but this works for negative infinity as well. So the limit of this rational function, that's going to be the same as the limit of this quotient, p of x over q of x. So now using the logic we talked about for the end behavior, this limit is going to be the same as just focusing on the two leading terms. So let's say the leading term for the numerator, the p of x, we'll say that's a sub n, x to the n, and then using the general notation, we'll do b sub m, x to the m. So then these two terms are the leading terms of my two polynomial functions. Okay, so now let's try this in an example. So the first one I have the limit as x approaches infinity of 3x squared minus 2x plus 8 divided by x squared plus 1. So what we just took a look at is that this limit should be the same as the limit as x approaches infinity of just the two leading terms divided by each other. So the leading terms are determining the end behavior of these two polynomial functions. Altogether, it's a rational function. So because I'm looking at x approaching infinity, I can just focus on those two leading terms. And now like this, I can simplify it. X squared divided by x squared will simplify to 1. So we end up with the limit as x approaches infinity of 3. And the limit of a constant is always just the constant, so our answer is 3. So basically we have this horizontal asymptote at the line y equals 3. Now, the other way we know how to handle this would be to write everything in that 1 over x form. So just to compare on what that looks like. So let's divide everything in that rational function by x squared. And then simplifying all those fractions, we have a lot of x's that will cancel out. So we end up with, in the numerator, 3 minus 2 over x plus 8 over x squared. And in the denominator, we have 1 plus 1 over x squared. So now here we have the situation with 2 over x or 8 over x squared, which are the basic limit properties we talked about for limits at infinity. So what we end up with, 2 over x, this will approach 0. 8 over x squared, that will approach 0. 1 over x will also approach 0. So what we end up with is just 3 minus 0 plus 0, and then divided by 1 plus 0. So different method, but we do end up with the same answer. Let's look at one more. So the limit as x approaches infinity of another rational function. So again, using our end behavior idea, this is going to be the same as the limit as x approaches infinity of just the two leading terms. Now I do have to be careful because in the denominator, it's not written in standard form, 5 minus x to the 4th. The leading term is the term that has the biggest exponent. So my leading term here is actually the negative x to the 4th. Okay, but again, just focusing on those leading terms, now we can simplify. So this is equivalent to the limit as x approaches infinity of 2 over negative x. And here's our basic limit property. So as x gets very, very large, this is going to approach 0. So our limit is equal to 0 here.